let's just answer a question from the class. So there was a question about the exercise hours. And they're Tuesday, 16:15 to 17 here. And also Friday, 10:15 to 11. And there's 2 student assistants in this course, and they will help you out with anything you ask of them. I guess you can't expect them to be prepared to answer questions for the last exercise quite yet, of course. So this week is exercise 1, I guess. But you could ask questions about any exercise in principle. Yeah, and they're both here in R10. And it's best if you try to split up so that there's more or less half of you go to one of them and half go to the other, but I guess that's hard to organize. So I really encourage you to work on the exercises, because even if there's no compulsory hand in, there's nothing you need to get approved to take the exam, I would still encourage you to work on the problems, because otherwise I don't think you will get a feeling for what is a multipole expansion, what's the Laplace equation, and I don't think you will be able to answer questions about them on the exam, because in the end you will need to be able to do calculations on your own. So any more questions about the exercises or anything? Midterm project? Nothing? Okay, I think that today the multipoles went a bit fast, so we'll finish a bit early. So if you have any questions about the first part of the course, just try to think of that and write them down, and we'll take the time to answer them if someone can think of something from anything we've gone through so far. Okay? Okay, so we were in the middle of this multipole expansions, and so well, if you're at large distances, the first term will look like this. And now because this is because, well, P0 is equal to 1. So the first Legendre polynomial is really simple. And then this is just the integral, and in the expansion. And of course that's equal to the total charge, because now I just integrate over the charge density, summing it up, and I end up with the total charge. So as a first approximation, far away from the charge distribution, it just looks like a point charge. But now, what if Q is equal to 0? What does that mean? Well, that means that we have to go to the next term in the expansion to find the leading behavior of the potential for large R. And that goes like this. And I call this a dipole field, because it looks like a point dipole. So it's r prime cos theta prime rho of r prime. And this is now called, let's see, this integral now is called the dipole moment. So I can write this as 1 over 4 pi epsilon naught p dot r hat over r square. So as you can see, For the monopole term, it's 1 over r for large R, and here it's 1 over r squared. And there's of course a cosine theta in this dot product, which gives an angular dependence. But still we say that the leading behavior for large distances is 1 over r squared. So of course if r is very large, then the monopole term is going to be more important than the dipole term. But if the monopole term happens to be 0, then this is the leading term. Yeah. And let's see. You know, the dipole moment is actually defined as the following precisely. This is essentially r hat dot r prime. I can move the r hat outside. So the dipole moment becomes the following. The integral over the charge distribution multiplied by the r prime vector. So the multipole moment is in fact a vector which points, well, let's see. Maybe we could do an example with this integral, so you understand what it is. Now let's consider the case that we looked at before. I'll put one point charge at plus d and one at minus d. And now the integral looks like the following. The dipole moment equals the integral over d3 r prime. And now what am I going to put in here for the charge distribution? Well, I could put, as these are point charges, I could put one delta function for each. So there's one delta function with a positive sign for this one. And there's one for the plus, no, the minus charge down here. So that's a minus sign. So I'm going to put this up here. So I'll just say Q and delta minus delta. So it's these two terms. And now this turns into a sum. And by the way, I think in general it's a good idea to remember, if you want to remember formulas, which you shouldn't need to, but in case you want to do that, you should try to remember and understand the ones with integrals. Because if you're thinking, I have to remember the integrals for the continuous and the sums for the discrete, well, that's not true, of course, because I could just put delta functions on all the point charges or line currents when you get to magnetics, and we'll get right back to the sum after doing the integral. And now, of course, the integral is very easy because it only picks up the function at these 2 points. So let's see. So if I put the origin here, I'll call this d vector. Then p is equal to d vector times 2, because this time I put it as the distance d, both above and below. So the total distance is 2d times q, the charge of the two, of the 2 point charges. So that's it. And also I'd like to make a note that the leading term in the expansion is coordinate system independent, meaning that the monopole moment, which is essentially q, the total charge, it's of course independent of where I put the coordinate system. But the dipole moment is not. So if you want to check this for yourself, you can consider the following example. So let's say I put a point charge with the charge value of q here and 3q there. So now let's see, maybe minus q. So now the net charge is 2q. So there is a monopole term. Now the dipole term is going to be dependent on, the dipole moment is going to be dependent on where I put my origin. So you could just try out, and this is just a sum, right? So it's very easy to do on paper. Let's say if I put origin at two different places, maybe I put the origin, okay, maybe I put the origin here, inside the 1 point charge. And then I'll try again with the origin inside the other point charge. So now you can see what are the dipole moments. Well, they're going to be different. So if someone asks you, what's the dipole moment of this charge distribution, then you have to ask them back, well, what coordinate system do you want to use? So this is a general rule that the leading term is always coordinate system independent. But the second, third terms, they will always depend, or at least usually depend on what coordinate system you choose. So make sure you don't get burned by that. Did someone have a question about this? It's okay to ask, as always. Yeah.
The leading terms always depend on the dipole moment, or was it just?
No, the dipole moment could be 0. For example, for the pure quadrupole. Now you can see that when you sum this up, you get one dipole moment here, which is a vector. And then you get the same vector opposite sign. So when you add these vectors up, which is essentially what the integral ends up with, then you see that the sum is 0. So now the quadrupole term is the dominating. So the leading term is not dipole if the dipole happens to be 0. But otherwise it will be, right? Because the dipole is 1 over r square and the quadrupole is 1 over r cubed. So if I go far away, it's always going to be the term with the lowest power here, which dominates. Same always. Yep. Yes, because if the monopole term is the leading term, well, the monopole term can only be the leading term, right? So, and the leading term is coordinate independent. That's a general rule. But also, the monopole moment is just the following, right? So it's just the sum of the charges. And of course, the sum of the charges, it's the same if I stand here or over there. If I have 5 electrons, the sum is going to be 5.
So there's no possibility, it's because of the possibility that you can only have 0 or cube.
Yeah, okay. The only possibility for... No, I'm not sure if I understood the question.
I integrate volume that it has the q in it, or the charges. And you get the q, and if you integrate over volume that is somewhere, don't know where, there's no q in it, then you get 0.
Yeah, right. So I'm not sure if I understand the question, but of course, if the part of space I'm looking at has charge in it, and there's a net charge, then this term is going to dominate, because it's 1 over r to power 1, right? So if I go far away, that's going to be the biggest term, no matter what the coefficient in front of the 1 over r is going to be, because I could always go so far away that 1 over r cube is, or square is going to kill off the dipole and quadrupole terms. And also, of course, well, if I have a charge distribution here or over here, well, the total charge in the distribution is the same no matter where I put it, in the sense that if I change the coordinate system, the total charge should still be the same. So does that answer the question? Yeah, okay. Anything else? Before I wipe out the blackboard? Okay. Now I'm going to show you a slightly different form of the multipole expansion, which is different from the one in Griffiths, but it's in the lecture notes, of course, and it looks like the following. Like this. Now it's 1 over epsilon 0, sum of L from 0 to infinity, m equals minus L to L. And now if you remember this is of course the sum over the YLMs. There's R to minus L minus 1, and then there's this QLM, and some normalization factor. So this QLM now, it's called, let's see, it's called the multipole coefficients. And now this is different from last time because if you remember the formula we had before, we had the charge distribution, we had the R prime, and R pointing out to the well, the point we're looking at, and theta prime is the angle between these two vectors. So now, if I look at P prime, which is a different point in space, then I'm going to have to redo the integral because I essentially changed the coordinate system by moving the r. I changed the value of the theta, right? So I have to redo all the integrals for each point I'm looking at, and that's a lot of work. Now this one is more, this is different because now I just set inside the charge distribution, I just set a coordinate frame, and I keep that fixed. And now for these, for different points, r theta phi in space, I could just sum up this series because the QLMs now are constants or well, coefficients. They don't change if I move around. So this is more convenient because now the QLMs, of course, I have to find them by solving integrals. But once I solve those integrals, I can use the QLMs forever, every time I want to do the sum. So I'll write down the formula for the QLMs. Like this. So it's essentially, well, from quantum mechanics, it's a dot product between this function, this one, and the charge distribution. So I expand the, because these form a complete set, I just expand the charge distribution in terms of these YLM functions. And now, as I said, I solved this integral once, and I can use it at all the points in space, both at P, P prime, and difference points. So I don't have to redo all the integrals as soon as I start looking at different points in space. So that's nice. And And this star is related to our expansion by the following following formula. Well. So now I have this prime PL Legendre polynomials. These are the Legendre polynomials of cosine of theta prime, but I want them in terms of well, theta and phi over here. So this is the following. Right. And there are no primes here. So now I can, if you use this, you can get back to the other expansion I showed you. Yeah. So I wouldn't spend too much time on connecting those two. The star here is complex conjugation because, as you remember, the YLMs had e to the power I m phi in them, so they might be complex. Or they will be complex also up there. So this is essentially the same thing, except that it might be more convenient just because that as soon as you evaluate these QLMs, you can use them for all the points you're interested in looking at. The price you have to pay is, of course, that you get a phi dependence and spherical harmonics, which are more complex than the Legendre polynomials. So, but of course, we recognize the structure that you have r to minus l minus 1 here. So hopefully, as we go far away, the first few terms will be good enough to approximate our potential. Any questions about this? So as an example, I'm just going to show you a bit more details about the dipole field. So we know the potential because I showed you in the previous lecture. Now, this is the potential, but of course in the end I'm usually interested in the electrical field, so I'll do the gradient to see what that looks like. And I'm going to stick to spherical coordinates. And these are, of course, unit vectors, if that was unclear. The one with the hat. Now, of course, there's a rotational symmetry here if I put the charges on the z-axis. So that means I can just neglect this term. And the result is the following. So there's one component in the r direction and one in the theta direction. And I can sketch the field by throwing up some field lines. So now I'm looking at a point dipole. So I increase the charge, decrease the distance. I increase the charge, and decrease the distance in such a way that the monopole moment is, the dipole moment is constant, and that's the way to construct a point dipole. And now the point dipole, or which could be some finite size dipole, just I'm far away from it, so it looks like a point dipole. From that field is going to look like the following. This looks somewhat like if you put a magnet beneath a sheet of paper, and then you put these iron filings on top, you can see something like this. And that's of course because all magnets are dipoles. So the iron filings tend to align along the field lines of the magnet. So yeah, and then we could also write this field in a coordinate-free form, which eliminates all the thetas and so on. So it's easier if you want to do coordinate transforms, and that's an exercise for you to show in the book. So that's not very important, but it's a nice mathematical trick because now you can see there's no theta, there's no x or z, y. It's just the vectors all along. So that's a nice property. So I think I'll just restate the whole idea of the multipole expansion. Let's see. So the idea we started out with was that if we have some localized charge distribution, now can I find an approximation for the potential V at large R? And now, of course, the immediate response might be Taylor expansion, for example. That's not very convenient because it typically assumes that x is small, right? For example, if you have, I don't know, if you have some function, you expand around some point, the first approximation is the linear approximation. And it's really good if you're close, but if you're far away, it doesn't mean anything. So the Taylor expansion is not, it's not a good idea. It's a good idea if you're close to the point you're expanding about. But now we want to look at sort of, if I go far away, at infinity, what goes on then? And then the answer is, of course, to use the multipole expansion. And if we go back to see what it looked like. It looks like the following. Like this. So As you can see, this is a series expansion, but unlike the Taylor expansion, it's in inverse powers of r. So as I increase n here, the term should get smaller and smaller at large r, because this is essentially some constant which we can calculate times 1 over r. It could be 0. And then some constant times 1 over r squared, which could also be 0, but might not be. And then you see as r becomes large, then the next terms become really, really small. So hopefully we could just say stop here, throw away the rest, and the first few terms will be a good approximation. That's the goal here. So I think we reached that goal by getting this series. So are there any more questions or comments about the multiple expansions, or anything we've gone through so far in the course? Why do we use
dipoles for antennas for radio?
Okay, so the question was if we have if the monopoles are stronger than the dipoles, why do we use dipoles for antennas? And well, you need to mix in time dependence together with this, but the answer is that the quick answer is that static charges, they don't emit any radiation at all. So you couldn't, in electrostatics, you can't get any radiation out really, because radiation is the stuff that goes to infinity. Now, but the thing is, if you have a dipole, you can actually, when you have time dependence, you can actually get potentials that have this 1 over r dependence. And also then you don't need to have any net charge anywhere, because you only need a dipole moment. So that's why, I guess, dipole antenna might look like this. So if you have some power source, then you have an oscillating power into the antenna, then you get, well, it's a dipole moment here because there's positive charge, negative charge, but as time goes by, these cycle through plus minus, right? So it's a good question, but I think we'll leave the details for the final chapter on radiation. But the point is anyway that you need some sort of accelerating charge to get radiation, and you can get that by point charges. For example, in particle accelerators, charges travel in a circle, right? So they're accelerated towards the center, and then they typically emit radiation front and back. If they're relativistic, they typically emit most of the radiation going forward. So you could get radiation from monopoles too, but it's usually less convenient for antennas. So I think we'll leave the details for later. Anything else? There's still 10 minutes left, so something you didn't understand in the previous lecture? Okay, that's good. Nothing? Or it's not true either? Okay, so good luck with the exercises on Friday. I didn't see a lot of people here yesterday, so I expect to see more people then. So, and have a nice weekend.